Thank you for joining us today for part one of the GastroPlus lecture series, Basic Model Considerations and Food Effect Predictions. While we allow some time for people to get connected, and before we start sharing our screens, I wanted to mention a few housekeeping notes. For optimal video and audio connection, we recommend you close out any additional web or streaming applications that may affect your internet bandwidth. We take your privacy rights seriously, and by attending this event or participating in the Q&A sessions, you're allowing us to contact you for follow-up. Today's webinar is being recorded for future playback on our website and YouTube channel. Today's session will run with a 20-minute lecture, followed by a rapid-fire 10-minute Q&A. Then Jim will guide us through real GastroPlus examples, followed by another 10-minute Q&A. For the Q&A sessions, you may ask questions at any time via the questions panel on your dashboard. If you need assistance, please use the hand-raising icon. We know there are lots of ways to spend your evening, morning, and everything in between. So on behalf of everyone on the GastroPlus development team, we appreciate you spending the next 90 minutes with us. As a special treat, we've invited Aditya Marfatia from Electrolab, our software distributors in Mumbai, India. Aditya, please tell us a little bit about Electrolab.
Hi, thank you so much for the introduction. I will take a few minutes of your time to talk a little bit about Electrolab. We have been established in 1984, and we are primarily a manufacturer of pharmaceutical testing equipments and peristaltic pumps. We export around 50% of our production worldwide. We have 250 plus colleagues in our group, with around 80 plus of them being in full-time sales and service support across India. Our reach is, we have around 21 patents for our innovative technologies, and with around 11,000 plus dissolution systems installations across the world. And as I mentioned, we are present in around 85 different countries. Our product range really falls into three different verticals. First being dissolution testing, where we manufacture dissolution testers, media degassers, diffusion cell apparatus, and the rotating bottle apparatus. The next vertical would be physical testing, where we manufacture hardness testers, disintegration testers, friability testers, and sieve shakers and tap density testers. And the third vertical, for which SimPlus belongs, is on informatics, where we've been working with SimPlus for now over 3.5 years, and we've had a wonderful collaboration. We also distribute SBAC software, which is a German company within India, as well as Cloudbase, Cloudface, and eLabDisso. We are very proud to mention that we are present in 48 of the top 50 Indian pharma companies. Like SimPlus, we also believe in giving back, through which we have a grant called the Effort Grant, which really starts for Electrolab Foundation Fellowship for Research and Technology grant, which provides funding for research projects for students. It allows an opportunity for certified internship, industrial visits, and hands-on training and demonstration with various aspects of what we do. So with that said, I would hand it back to you, and thank you for the opportunity to talk to everybody today. Thank you.
Thank you. That was a great presentation, Aditya. We appreciate you being with us today. Now, to get started, we have a quick poll question for you to tell us a little bit about yourselves. How familiar are you with GastroPlus software? We'll give you just a few seconds before we start the introduction with Jim Mullin. We're going to go ahead and close the poll now. And it looks like most of you are somewhat familiar with GastroPlus, so that's fantastic. Now, I'd like to introduce today's speaker, Jim Mullin. Jim is Senior Principal Scientist at Simulations Plus, currently working on finalizing GastroPlus version 9.8 and improving the population simulation features of the upcoming GPX. In addition to the development of computational models, Jim also contributes to several FDA and EMA collaboration grants for Simulations Plus. He's an avid hiker, prolific investor, and a cat person. Today, he's going to share with you why you should be using GastroPlus to integrate your in vitro and in vivo data to develop PBPK models used to support regulatory decision-making. So without any further ado, I would like to welcome and kick things off by sending it over to Jim. So let's get started.
Alrighty, thank you, Arlene, very much for the introduction. As mentioned, my name is Jim Mullin, and today I'll be talking to you about the food effect. So let's get right to it. The BCS classification system predicts the likelihood and direction of a food effect 60 to 70% of the time. So for class 1 drugs that are very soluble and have very high permeability, there is typically no food effect. Why would there be, right? They're fully soluble in the lumen and they're highly permeable. So we generally see no food effect there. With class 2 drugs that are low solubility but high permeability, 71% have a positive food effect. This is because of the poor dissolution rate caused by the low solubility. When the drug is taken in the fed state, the dissolution rate is improved and the solubility is improved because of the additional bile salt micelles in the lumen. Class 3 drugs have, in general, a negative food effect. These are a little bit harder to predict in general with the software, but we'll show you an example today where we can do that and show you some additional info about that. But 61% of those class 3 drugs have a negative food effect. These are highly soluble drugs that have low permeability. Of course, the reason they have low permeability is because they're very polar. Their permeability may be enhanced by excipients or other such transporter effects, and so this is why these are difficult to predict. The last classification is the class 4 drugs, which are again low solubility but also low permeability. And because they're low solubility, again, the positive food effect is most likely predicted, and this is because of the solubility and dissolution effect. Again, even though they have low permeability, they need to be soluble to be absorbed. So the increase in the bile, again, has a major effect in causing the positive food effect there. Of course, there's many different papers that have studied this effect, and this is a paper from the FDA where they looked at the GastroPlus simulations in the fed and fasted state for PO doses of carbamazepine. You can see that for the suspension, there's minimal fed-fasted effect. In a suspension, it's likely going to be, less dissolution rate limited, so you see less of a food effect here. But they had an IR tablet where they showed a pretty large food effect in AUC, and then also you don't usually see too big of a food effect with the XR type formulations because the dosage form controls the release and not really the bile salts in the lumen, right? It's generally you're targeting release later on in the colon and whatnot, so you generally don't see as large a food effect. So in this study, they looked at the fasted and fed kinetics and were able to predict that very well just based on particle size and bile salt concentrations in the lumen and the enhancement in solubility due to the bile salts. One thing that you also see for these class 2 drugs for the impact of particle size under the fasted and fed conditions are you generally see very little sensitivity to particle size in the fed state. So in the diagram below, I believe this is the same study, but if you see the diagram below, in the fed state, carbamazepine, really there is no sensitivity to the particle size because the drug is much more soluble with the higher increased amount of bile in the lumen. So very little impact of particle size. Now, if you look at the fasted state, which is A up on the top part of the diagram there, you see a very strong relationship with particle radius and the concentration in vivo. So, you know, obviously, if you want to minimize the food effect, you're going to reduce the particle size in this case so that you get something, oh, it looks like just visually something closer to 1 micron would give you a dosage form that's, you know, doesn't have a food effect in this case. So you can sort of design out the food effect if you optimize or tailor your particle size to give similar exposure in the fed and fasted state. And here's another example from Hannah Jones in 2006, a basic compound where they looked at the fasted and fed state kinetics for a 10 mg and 50 mg dose and showed that the predictions in GastroPlus were good for the normal fed state. However, they had to boost the solubility for higher bile salt concentrations in the high fat fed state. So this is one of the data sets that led us to sort of you know, evaluate maybe adding some new high fat settings, low fat settings into our GastroPlus simulator to better deal with the fed fasted effect when we have different meal types. So keep that in mind. We'll talk about that here in a few slides. So what changes are accounted for between the fasted and fed state models in GastroPlus? So if we look at the GI physiologies for GastroPlus, we'll find that the main contributors to the fed fasted effect are going to be the transit time, the pH of the stomach, the volume of the stomach, and then the bile salt concentrations. So those are the main changes in GastroPlus. There's also the effect of the higher liver blood flow, which has to manually be changed for the PBPK models. If you're using a compartmental approach, that'll be adjusted automatically here in the QH field over on the right-hand side, this yellow box here. So these are the main drivers that cause either maybe a negative or positive food effect for your compound. Of course, the bile salt concentrations directly impact the solubility in the lumen via the Matheny equation from 1996. This was published, where you have the bile concentration multiplied by a solubilization ratio and the solubility in the aqueous phase, and that will determine the solubility in the lumen. So this is the equation that we're using. Of course, you can also supply in vitro data for a solubility at a given bile concentration, and then you can actually back calculate the solubilization ratio as well, and that's an input into our GastroPlus model. You can also predict that with ADMET Predictor, and so this allows you to utilize, you know, either in silico predictions or your in vitro data. Of course, we've gone further. So in the last version, GastroPlus 9.7, we've added some additional built-in fed physiologies for different meal types. So you can see the transit time here on the left-hand side has been adjusted up from 1 hour to 2.45 hours. And you can see the bile concentrations have been increased as well. And we've turned on zero order gastric emptying. So these account for the fat content in changing the bile salt concentration and actually link gastric emptying to the calories of a meal. So this is where you can now click on this fed meal option. You can select fed state model, there's, I think, 10 different defaults. The FDA breakfast meal, which is, I think, around 950 calories, and I want to say 40 to 50% fat, somewhere in that region, off the top of my head. And then we have a bunch of different built-in types, like low fat, low calorie, high fat, high calorie, and everything in between. So you know, we have basically everything you might want to, I guess, test on your own when you're looking at these fed state physiologies. So the data that's used to adjust the fed state based on calories comes from a variety of different literature sources, which we're summarizing here in the graph on the left-hand side. So we compiled literature from probably 20 to 30 papers and looked at the gastric emptying half-life versus the calories of the meal. And we found a very good correlation with the calories. On the right-hand side is the meal volume of those meals in all those studies. And so we're looking at the gastric emptying time versus the meal volume. And it turned out we didn't really find a very good correlation in gastric emptying with the meal volume. So we're not accounting for differences in meal volume. Obviously, you can set the initial volume of your meal in GastroPlus, but that's not going to impact the gastric emptying half time that's input into the model, because it wasn't well correlated when we looked at the data. Of course, there is some other factors that can modify the gastric emptying, like the maybe fat, protein, and carbohydrates of the meal. However, there wasn't a lot of data regarding that, and it's a much smaller impact, so it's not currently considered. But that's something that we are looking to add in the future, and maybe also the impact of the meal on the pH of the stomach as well. Obviously, a meal with maybe higher protein and maybe some milk solids might have a higher pH than a normal meal. So these things can be accounted for in GastroPlus in the future, hopefully. So the data that we use to adjust the biliary concentration in the lumen in GastroPlus is from the Marciani paper. I'm not as well, that's one of the papers that we looked at, and it shows an increase in the amount of bile that's excreted with different fat amounts. I think this was a milk-based beverage. So you can see from 1.5 grams of fat to 10 grams of fat, you see the volume change in the gallbladder change quite a bit, right? So for the lowest fat, you see the lowest volume change of the gallbladder, and then for the high fat, you see the highest change. And so this, we need to sort of correlate with the luminal concentrations of bile. And so we took some other data from Reddy as well, from Cancer Research in 1981, and he looked at feces bile concentration based on diet. And we have a bile concentration spreadsheet model that was developed originally to determine what the luminal concentrations of bile were for our GastroPlus ACAT model. So what we did was look at the different levels of bile production that we sort of predict from this Reddy paper and the Marciani paper above, and we model 3 meals a day and then a big long fasted state for the sleeping period, and we look at the overall bile based on these different changes in biliary excretion, basically. And we come up with, at different fat levels, different concentrations, steady state concentrations of bile based on our bile salt model. Of course, our bile salt model takes into account the volume of each compartment in the intestine. It takes into account the excretion rate from the bile, or from the gallbladder, and then it takes into account the reabsorption rate from the intestinal segments. And so that's how we're able to make these predictions. And from these predictions, these were generated for our new fed state models. So this is a table of what those values are. And here's a couple quick case studies about our fed state model in terms of our new predictions for the calories and the fat content of the meal. So the first one is axitinib. Axitinib is a lipophilic based compound, and it's a pretty good compound to use for this type of case study because it really is sort of gastric emptying rate limited. So you can kind of see the appearance in the bloodstream sort of tracks the gastric emptying because it's high permeability and high solubility in the gastric. Precipitation doesn't occur even though it's a weak base, so that's another thing that sort of aids in analyzing what's going on with the fed state model and the changes in the gastric emptying versus calories and whatnot. So the next slide is the fasted state baseline model, and then the fed state model with the old GastroPlus 9.6, where we don't correct for any sort of transit time effects of the meal calories and that kind of thing. So just the standard default settings from GastroPlus, and you can see that we really do a poor job of predicting the appearance rate of drug in systemic circulation for axitinib and the high fat meal type because the gastric emptying is simply too fast using our default settings. And that's shown on the left hand or the right hand side here. On the left hand side in the fasted state, you can see that we do have the correct permeability and whatnot because we see the appearance rate is sort of matched for the fed state. So we know this appearance rate in the fed state is clearly due to gastric emptying. So if you then use a fed high fat meal, 900 calories, where the bile salts are increased and the gastric emptying is increased, and we use the zero order transit, we get a much better prediction of the appearance rate in systemic circulation for axitinib, as shown in the right hand side. So you can also use the normal meal, and that sort of over predicts Cmax because the transit time wasn't long enough, but the high fat meal seems to do the job here. So this is sort of validating the approach that we really do need to, for a lot of these studies, increase the gastric emptying time and increase the bile salt concentration to sort of match these data sets. And here's another case study. We can't mention the compound because it's proprietary, but this was another case where the default fed state method in GastroPlus 9.6 was underpredicted in terms of Cmax, and the Tmax was maybe a little bit predicted a little bit too early. And in the case of the FDA standard breakfast, we were able to much better predict the initial rise of the plasma concentration and match the time points much better between the fed state with the FDA breakfast and the default GastroPlus 9.6 settings. And then we were also able to predict better the Cmax in terms of the new FDA breakfast settings. And if we look at overall, we've done sort of 8 validation studies for this these new settings where we had data in the literature to do so, where they looked at different meal types. And so across all those studies, about 6 out of the 8 studies were better predicted using the new zero order gastric emptying and zero order transit times that we predicted based on calories and the meal types provided in those studies. So you can see here for dulaglipir, axitinib, and 4 different internal studies. The original GastroPlus settings didn't work well. The new settings worked much better along with the breakfast setting, or the type of meal that was given in the study worked much better than the default settings. For a couple compounds, the default settings worked better. And so, but for the preponderance of evidence shows that the new settings are much better. So that kind of goes through the theory section that I wanted to talk about. So that'll open us up for the first question and answer period. I thank you for your attention in the first segment there, and shoot with your questions and I'll try to answer them.
So today it gives me great pleasure to introduce today's moderator and recognized PBPK modeling expert, Kay Zito. With boundless energy and passion for mathematical modeling, she currently leads several PBPK-related consulting projects and the development of new physiologies in GastroPlus. K is also highly involved in the refactoring process of GPX, whose goal is to provide a streamlined user interface at an accelerated modeling speed. With that, I'll quickly hand it over to the witty and talented Kay. Take it away.
Thank you, Harleen, for the kind introduction. And Jim, that was a great presentation. Here, I do have a list of questions for you. Are you ready to answer them? Here comes the first question. Yeah. Usually the higher liver blood flow is observed in fast state. Is that accurate?
Yeah, correct. In GastroPlus, we changed the liver blood flow rate for the compartmental model as well as the PBPK model. Now, you have to do it manually when you set the PBPK model settings. So I think in general, the liver blood flow is increased about 1.4x, if I remember correctly, is a good rule of thumb, 1.3 to 1.4x. And yeah, so that's already done automatically if you're using the compartmental model, but you have to do it manually in the PBPK settings. So, but yeah, that's what you would do to account for the fed state. You do want to increase the blood flow.
Okay. Second question, what is the impact of low-calorie, high-viscosity meals?
So we don't really have any viscosity setting for the meals currently. However, we'll get into an example in this next slide. The next section where we talk about the examples, we're going to go through an example of how you would correct for like the meal viscosity. So that's generally going to affect maybe the dissolution rate or disintegration rate of your dosage form. And so we're going to go through an example where we show that just here in a few minutes. So I would stay tuned for that. But I would say that the modifications you would have to make in GastroPlus are mainly related to the dissolution rate that you provide the software. So, and as I said, we'll go through an example of that.
Thank you. And what about poor soluble drugs? How could we optimize the food influence in the PK predictions?
So currently, right, our our software is set up to do a prediction, right, based on the solubility. So it'll become more obvious when we look at some of the examples. There's a few inputs that you need to provide in order to get the right sort of predictions for poor soluble drugs. You need to measure the FASF and or FESF solubility. So that would be the solubility in bile salt micelles, and you need to add that to the model. Otherwise, you can't really make a good prediction. So you can predict this also using AdMet Predictor, our software product for predicting properties from structure. So our prediction isn't really an optimization. If you want to go in and optimize a specific model, you can use our optimization module. If you think that one parameter needs to be adjusted to better fit your data, you can go in and do that. But in terms of the predictions in GastroPlus, you're not really optimizing anything. It's all predicted based on some in vitro data that you provide and whatever dissolution parameters and inputs to the model. So we make a prediction, from theory about what the increase in exposure is in the food effect, and you actually don't generally want to optimize the food influence. You want to minimize the food influence, right? You want your fasted state PK to be the same as your fed state PK. So the way to do that is to usually optimize the formulation, make it dissolve faster, reduce the particle size, as I mentioned earlier. So in terms of optimizing the food effect, you kind of want to get rid of the food effect, right? If you're when you're formulating a drug. So our software allows you to do that, determine what sort of size particles you need or what sort of dissolution you need to reduce the food effect. And we'll get into an example of that in the next presentation. So
yeah, great. So could you please tell us a little bit more about the zero order entering and then transit time model?
So there's two types of gastric emptying, right? There's first order, which is exponential. in shape, right? The differential equations are first order, which means they're first order in time, and it's in it when you solve the differential equation, it forms an exponential function. Zero order means it follows basically a linear sort of not release, but emptying rate. So it follows sort of a linear profile. And it turns out that most of the fed data for transit time seems to indicate more that the emptying looks more like a linear type function or a zero order function than a first order function. So we do know that in the fasted state, at least, the emptying is more exponential. But from what we've seen from the literature, the zero order emptying seems to better predict the fed state, and it also seems to better predict the early rise of the PK data for fed state PK data. So those are the differences. It's just one's exponential versus one's linear, right? So that's it. That's really it.
Okay, yeah, thank you. So there are a couple questions asking about the class 4 compounds. So usually the class 4 compounds pretty hard to predict for the food effects. Do you have any comments on this category of compounds?
So yeah, I mean, I guess if you look at the BCS classification system, it still predicts with a pretty high degree of accuracy, like 60 to 70%. That it's going to be a positive food effect for class 4 compounds. So they are more, obviously, they're a lot more variable and I guess a lot more difficult to model than class 2 compounds because of the low permeability as well. But in terms of the predictability of the food effect based on the BCS classification system, it's still a pretty good correlation, right? You can pretty much be assured most of the time that it's going to be a positive food effect for a class 4 compound. Now, if it's the standard, if that's caused by, well, that's caused by the increased solubility, right? In the fed state versus the fasted state where the solubility is lower. So that's what causes the positive food effect for class 4 compounds. And we can predict that food effect. That's not super hard to do. The thing where class 4 compounds where we probably might have a little bit of a problem is maybe some types of transporter effects, if any of those are, if there's any basically transporter effects in the intestine, really, because these drugs are not very permeable, right? So one of our body's mechanisms to get these drugs permeating into tissues is to, they're substrates for transporters oftentimes. So that's any of those effects are going to be harder to predict with our, fed state predictions.
Yeah, thank you. And then how would you account for the excipients effect on the overall drug release?
Yeah, so currently we don't have tons of excipient models in GastroPlus. We don't track the concentration of excipients. We have just recently, and I think this is coming out in 9.8 as a new feature, we're going to have cyclodextrin formulation models. However, we don't have, like, let's say you put SLS in your formulation, or you put something like that that may enhance the solubility. We don't currently track those. So while you could adjust the dissolution rate based on some in vitro data because of these excipients, we don't actually track the concentrations of them. So you have to account for it through the dissolution rate that you provide the software.
Okay, thank you, Jim. Because the time, so we're gonna close up the first Q&A section. I do have a lot of questions for you, but we'll save that for the second Q&A section. So I'm gonna pass it to Arlene.
Thank you, Kay. And we're gonna go ahead and Jim, get started with part 2.
In this next section, we'll be doing a hands-on demo of GastroPlus. We'll be showing you how to predict the positive food effect with this compound X example. And then for the second example, we'll be looking at the negative food effect for trospium hydrochloride. So compound X is a BCS class 2, maybe class 4 compound. It's lipophilic with a log P greater than 4, and it's got two basic pKa's of 3.2 and 6.2. The solubility is very low, obviously at about 1 microgram per mil, and it's pH dependent. So you can see on the plot on the lower right, the solubility drops off by 3 orders of magnitude from pH 2 to physiologic pH at about 6.5. For this compound, 70% of the dose in the fasted state is recovered in the feces, and the bioavailability is around 30%. And this is indicative of probably the drug not being able to absorb in the intestine, and so it's just getting excreted in the feces. This paper was from Tycho's group and Novartis, and so I thank them for the data here. They provided all the physicochemical properties and the pharmacokinetic properties for this drug. So we'll be using all these compound properties in the upper part of the table for molecular weight, log P, pKa, solubility. They also provided biorelevant solubility, effective permeability, and particle radius for this compound. And then we don't have IV data, but they did graciously supply all the pharmacokinetic parameters for a 2-compartment model shown down here in the bottom of the table. One important aspect for this compound is the high lipophilicity and the 2 basic pKa's at 3.2 and 6.2. This is indicative of a compound that's, again, highly soluble at low pHs, but poor solubility at physiologic pH. This is a compound that will likely store in the lysosomes of the cells because lysosomes are at a low pH versus the cytosol in the cells. So this is what the next slide is getting at, describing here, lysosomal trapping of lipophilic cations. So if a compound is highly lipophilic and has basic pKa's, the drug tends to permeate into, this diagram is for hepatocytes, but this is also true for the enterocytes in the intestine, lung tissue, brain tissue, any type of tissue with lysosomes present. The drug will permeate into the cell, into the intracellular space where the cytosol is at a pH of 7.2. And at that pH, it's mainly neutral, right? Based on the pK. Well, in this case, the compound has a pK of 3 and 6, so it would be mainly neutral at cytosolic pH. If the drug then permeates into the lysosome where the pH is 4 to 5, the drug is going to convert into the charged form or the positively charged form. So the solubility is going to be way, way higher in the lysosome than in the cytosol. So the drug is going to tend to migrate into these lysosomes, and it's going to store there rather than permeating the intestine and getting into the bloodstream. So what happens is this leads to an extended Tmax for these types of drugs. And so this is what happens again with compound X as well, because it's lipophilic and has the, it's cationic and has the 2 basic pKa's. So for the activity, we're going to open up GastroPlus, and I'm going to explain to you up front what we're going to do here in this example. So we're going to open up the database for compound X. We're going to navigate to a fasted record and look at the PK of the 200 mg dose of compound X in the fasted state. We're going to look at how to train the model for the lysosomal trapping and the precipitation. Because this compound is basic and the solubility is low in the intestine, when it transfers from the stomach to the duodenum, there's going to be a large pH change and a potential for precipitation. So we're going to look at that effect as well. And then we'll take those same parameters that we use or generate from the 200 mg IR capsule fasted record, and we'll use them to predict the fed state at 200 mgs and the fasted and fed state at 400 mgs. So we're going to use one data set to train the model, and we're going to predict on 3 other data sets in the fasted and fed state. In doing so, we'll see how we can set up the model to predict the PK in the fed state. So we'll look at the adjustments made in GastroPlus for the fed state and kind of review what we did in the first section, in the theory section. So we're going to go to the first record in the database, which is the 200 mg fasted record. We've entered in all the physicochemical information. So we have the log P, we have the solubility entered, we have the permeability entered from the paper, the particle size information. So we talked about correcting for the solubility in the lumen for the bile salts. If we click on biorelevant solubilities, this is where that information was added here. So you add the in vitro measurement for FASIF solubility and FESIF solubility, and then you click fit to in vitro data, and that generates the solubilization ratio that we talked about in the theory section. So this solubilization ratio is going to be applied in our model to predict the solubility in the lumen. And you can see here below it says the duodenal solubility at bile salt concentrations will be 0.022 mg per mil. And you can see that's much, much higher than the aqueous solubility, which is going to be somewhere around, maybe 1 microgram per mil. Okay, so that's the biorelevant solubility. We can click the pKa table, and that's going to show us our pH-dependent solubility. So we've entered in the pKa information for this compound, and we've fit the solubility factors such that we get a match to the pH solubility curve. If we click plot y-axis and solubility, you can see that we have a good fit across the range. And obviously, since this drug is more soluble in the gastric, right, whereas it isn't soluble in the physiologic pH, you have the potential for some precipitation for this compound. So we're going to look at that as well, right? Okay, so we've set up this simulation to run. We have all default properties currently. We're using the default precipitation time, and in this case, the default amount of lysosomal trapping, which is entered in to GastroPlus through the variable called fraction unbound in the enterocytes. So we'll look at how we could train this model to match our PK data. But first, let's run a simulation that's for this record before we've trained the model. So we'll go to Simulation tab. We'll click Single Simulation, and we'll click Start. It'll bring up a Start Simulation check window. We want to use the default settings, so we'll click OK. I'm going to click No. It's a capsule dosage form, but I don't want to change the stomach emptying rate. And you can see right here off the bat, if we look at our single simulation output summary, you can see that the Cmax is overpredicted and the Tmax is underpredicted, right? So I already talked about the Tmax, right? Lysosomal trapping would lead you to believe that you would have a longer Tmax for this compound because the drug is going to be partitioning into the lysosomes of the cells. That's going to slow down the appearance into systemic circulation because the drug is all partitioned into the lysosomes. The other thing you see here is that the Cmax is too high. Part of that is because of the lysosomal trapping, but part of it is also because of the precipitation. So let's just do this stepwise, right? First, we'll look at the lysosomal trapping, and then next we'll look at the precipitation rate. So we could just enter in a fraction unbound and optimize this. And the way to do that would be to go to the Simulation tab, and we could do a parameter sensitivity analysis. We could adjust the fraction unbound in the enterocytes, or the amount of drug bound to the lysosomes. We can look at the effect of that by just doing a single PSA. If we click in the simulation mode, the PSA button, it'll allow us to select the parameters and select the fraction unbound in the enterocytes or the lysosomal trapping. So we can select parameters. And I believe there's a lot of tabs here, and you're going to have to wade through these at times, but I believe the fraction unbound enterocytes is under the ACAT compound tab. And you can see this FUENT, which stands for fraction unbound in the enterocytes. And this is what you use to adjust for the lysosomal trapping. So let's select that. And the values are going to range from 0 to 1 for this variable. I'm going to adjust the baseline values. We already know that 1 is way over predictive or under predictive of the amount of binding. So what I'm going to do is lower this to about 0.1 for the baseline value, and I'm going to lower the lower bound to about 0.005 or 0.5%, and then I'm going to change the upper bound to well, we'll just leave it at 1. That's fine. And logarithmic is probably a good way to test this because we're going over a large range of parameter space, so logarithmic tends to work well in that case. So let's click OK. And now we could run the parameter sensitivity analysis. So we'll click OK. And we'll save it as the default file name. And now it's going to run the 10 different simulations with different fraction unbound in the enterocytes. And it'll hopefully show us whether or not we have a good prediction to our data. I think if we remember back to the single simulation I ran, I think the Cmax was about 0.3 and the Tmax was about 4 hours for this compound, right? So let's keep that in mind when we look at the results for this PSA. So we'll go to the graph tab and then we'll click the spider plot now that the simulation's completed, and we'll look at the Tmax in this case. So here you can see that as the fraction unbound decreases and the amount of drug in the lysosome increases, the Tmax is extended. You'll see that it doesn't really have an impact on the percent absorbed. So the fraction unbound in the enterocytes is just slowing the amount of drug getting in systemic circulation. It's not changing the amount of drug that's really permeating into the enterocyte layer. It's just slowing it down from entering the bloodstream. So the Tmax for this dose is about 4. So it looks like a fraction unbound of about 0.003 matches the data pretty well if you look at this plot here. So let's try that. So we could leave this open, but I'm just going to close it. We've gotten all the information that we need from this. So it's a little bit of a mystery to most people how to enter in the fraction unbound in enterocytes. It would be easier if we put that parameter prominently in the interface, but it's not something you adjust very often. So it's kind of hidden. In GastroPlus, it's under the database menu in the file bar, and then view and edit tables, and then view and edit drugs table. So here you're going to have to scroll over all the way about 75% of the way over to get to the fraction unbound in the enterocytes. So here we go. So you can see here percent unbound in the enterocytes. We'll enter a value of 3% for all the records currently. So we'll translate that to all the drug records and click save. And now let's run a single simulation with that 3% as our unbound in the enterocytes. And you can see that's already improved our simulation here. It's lowered the Cmax and it's improved the Tmax to align with the experimental data. Now, I'm not going to go through this software tool much, but we do have a method where we could predict this fraction unbound in enterocytes using a model. So Kay, who is moderating the chat and moderating the questions as well, gave a presentation a couple weeks ago about the MembranePlus software product. So I can't go into the details. Look at her presentation. It should be on YouTube or our website. But if we open up, I've already got a database set up for MembranePlus. So we can model the amount of lysosomal trapping using the mechanistic model in MembranePlus. So what it is doing is seeing how drugs sort of permeate through a CACO2 cell layer, and it's actually mechanistically calculating how much drug is entering the lysosomes and trapping inside the lysosomes. And so if we run this simulation for compound X, we get a prediction of not only the permeability, the concentrations in the experiment, so the receiver side on the apical side of the membrane, and then, the dose side or the apical side of the membrane, or the receiver side, the basolateral side. But we also get the fraction unbound in the cell, which is about 3.5% that's predicted here. And that correlates directly with what we see in our model for compound X. So we can, obviously fit it using the parameter sensitivity analysis in GastroPlus, but we also have this external tool, MembranePlus, that allows you to predict the amount of lysosomal trapping, and you can apply that to your model. So that's the link that you can have between this mechanistic in vitro simulation and GastroPlus. So let's go back to GastroPlus. So I also mentioned that this drug is it's also a base. So the solubility is low at physiologic pH. So also precipitation, right, is going to be potentially occurring, and is occurring in this case. You can tell by the PK curve when you have like a sort of extended hump in the plasma concentration curve like you see here. That's generally indicative of some precipitation. Of course, our default precipitation time is predicting about 50% of the drug is precipitating. So if you look at the red curve, if we click on the absorption and dissolution quick plot, you can see that a lot of the drug has precipitated and then redissolved, and that is slowing down the absorption a little bit because the drug is not available for it's precipitated. So but it seems like we have a little bit more precipitation than our default parameters would suggest. So again, we could do a PSA and determine how much precipitation is causing this reduction in Cmax. And to do that, we can again go back to our good old standby, which is the parameter sensitivity analysis. We could click the parameter sensitivity analysis button, and instead of looking at the enterocytes, we could click select parameters, and we're going to have to uncheck the fraction unbound of enterocytes, and we're going to have to go to the compound tab and click the, actually I think it is the, it might be, yeah, it's the compound tab, precipitation time. So, I've used this program for a long period of time, probably 10 years, but I still forget where some of this stuff is. So there's a lot of options, and you'll have to wade through them as well. So let's close that. We know 900 is already not good enough in terms of predicting the precipitation time. So I'm going to lower the baseline value to like 400 and set the upper bound to 900, and then we'll set the lower bound to 100. And we'll do two or 10 tests, and this one I'll do a linear. I don't think we need to do a log in this case. Click OK, and we'll click Start. And again, save it as the default name, and we'll then run the simulations and see if we can bring the Cmax down to about 330. I believe nanograms per mil. That's what we're targeting here. So it's completed. Let's click the spider plot, and we can then select, in this case, Cmax. And if we look at, our plot here, I think our Cmax is around 0.32 to 0.33. So if we look over to 0.32, we see the precipitation time needs to be about 370-ish seconds. And it's a little bit lower than that, so we'll go 350 in this case for the precipitation time. So let's close that down, and let's adjust our precipitation time to 350 and run a simulation, a single simulation. And now we have a Cmax that's in line with our experimental data, and we get a pretty good result here. So we'll then use this 3% fraction unbound in enterocytes and the precipitation time of 350 for all the different records. So let's go to the fed state record. I'm going to save my database by going to database save drug record. So I'm going to go one record over by clicking this right arrow to advance one record over. This is the fed state 200 mg capsule. And I'm going to adjust the precipitation time to 350 here on the main compound tab. We've already adjusted the fraction unbound and enterocytes. So now we can just run a simulation and see how well we predict the fed state. Of course, remember, we're doing adjustments for the transit time, the pH, the volume of the stomach, and then the bile salt concentrations are about 4 times higher in this case. So what we would expect here is that the drug is going to be more soluble, so the precipitation is going to be less, the dissolution is going to be faster, and it's going to lead to more absorption and a higher Cmax, higher AUC. So let's see if we can predict that. Let's go to the simulation tab and click start. And here you see that we're predicting a Cmax of about 683, and we're doing a pretty good job within the error bars, at least, in predicting the PK here for compound X in the fed state. So this predicts about a little bit more than a 2x or so increase in PK due to the fed state. We could also look at this for the 400 mg tablet. So let's advance to those records. So for the 400 mg, I'm going to again put in 350 for the precipitation time. And we'll just run a simulation to verify that that is working. And we see that, using our precipitation time and fraction unbound and enterocytes, we again get a good prediction of the fasted state dose at 400 mgs. And then finally, we'll go to the 400 mg fed state. So we'll put in 350 again for the precipitation time. Again, review our compartmental data. We have the fed state selected. We have the increased pH, transit time, volume, increased bile salt concentration, and then we'll run this simulation. And you can see again, we're predicting about a 2x increase in PK due to the fed state. So that's how to predict the positive food effect in GastroPlus. So one additional thing that you can do, we don't really have time to get to this because we have to move on to the negative food effect example, but one additional thing that you can do with this is analyze how you might design out the food effect for a given compound. So is there a way to adjust your formulation to have an optimal release so that you don't have a fed-fasted effect? Can you reduce the particle size enough and dose maybe to get 100% absorbed in the fasted state and the fed state? Because that will generally design out the food effect or cause you to have sort of a difference in Cmax or AUC closer to 1 for the fasted and fed state. So in GastroPlus, you can do this by performing a parameter sensitivity analysis. You can run a 3D sort of virtual DOE on the dose and the particle size, which is what is shown here. So you would click select parameters, you would select the dose, you would select the particle size, and then you would run the PSA, 3D PSA option. And the output from that is going to be a surface plot. So you'll get a surface plot showing you the effect of the fraction absorbed on the particle radius and the dose. You could do it for the fasted state, which is on the left-hand side, or you could do it for the fed state, which is on the right-hand side here. And you can see that kind of shifts the PK space. So if you look at the fasted state, you can see that the drop-off in fraction absorbed versus particle radius is much sooner in size than when you look at the fed state, right? You don't need as small of a particle size when you're in the fed state because the solubility is higher because of the higher bile salt concentration, and so the dissolution rate is faster. So you generally don't need as small of a particle size when you get into the fed state, and that's kind of what these surface plots show. So you can then see how mitigating, or you can see how reducing the particle size is going to mitigate the fed-fasted effect. So in this case, you would have to look at particle sizes of about 0.02 micron or so in the fasted state to get a dose that's fully absorbed. Whereas in the fed state, it may be a little bit higher than that, but maybe something more like 40 or 50 nanometers or 0.04 microns. Now, these particle sizes in this case are going to be much smaller than you could formulate given a conventional technology with crystalline drug. So you could do nanomilling, and that'll get you down to maybe 200 nanometers, maybe 100 if you're lucky, but I would say probably 200 nanometers is a good goal there. This is much smaller than that, so you would have to, in this case, I would come to the conclusion that you may have to then use a amorphous form to solubilize this drug to get design out the food effect. So this method here will tell you whether or not particle size reduction will reduce the fasted effect, and or if you need to go to some sort of enabled formulation to mitigate the food effect. And so that's the positive food effect example I wanted to go through. Next, we'll go through the negative food effect, and these are going to be in general much more difficult to predict. And so we'll go through this Trospium HCl example, which is a BCS class 3 compound. And this paper's from Peter Langeth from Mines, and they looked at the PK of trospium hydrochloride in the fasted and fed state. And this compound, again, is class 3. It's very hydrophilic, so it's got a negative log P of 1.2. It's got very high solubility. You would expect it to be freely soluble in water with that kind of lipophilicity. And it's got extremely low intestinal permeability, 0.07 times 10 to the negative fourth human permeability, human intestinal permeability. It's not metabolized, as again, you would expect that based on the EECS classification system. These types of drugs are going to be eliminated through either renal secretion or some kind of active transport mechanism. And then the bioavailability is very low because of the low permeability, sort of like 10%. So we're going to look at the fast and fed pharmacokinetics in this case. So before we look at that, we'll sort of look at some of the in vitro experiments that they performed on trospium. So they saw this negative food effect between the fasted and fed doses, and they wanted to explain that. So they looked at sort of some dissolution methods and solubility tests to look at what's going on in terms of, is the solubility of the formulation changing or the dissolution of the formulation changing? So in this first table here, they looked at a bunch of different media, SIF, just HCl, sort of a low pH buffer. They looked at dissolving HPMC into the buffer, and what that does is increases the viscosity. And when you eat food, right, it increases the viscosity of the stomach contents, and that is going to have an impact on the diffusion coefficient, right? So, I mean, this comes from theory, a Stokes-Einstein equation, right? Or Haydock and Laudy, an equation like that. That'll tell you that viscosity is related to the diffusion coefficient. So the speed at which drug is going to dissolve is going to depend on the viscosity. So in the stomach, where you have high viscosity, maybe something similar to 2% HPMC, you're going to see maybe the dissolution decrease because of the diffusion coefficient. But here they were just measuring the solubility, and they saw that the solubility actually decreased a little bit for the formulation. Of course, these solubilities are so high it's not going to matter in terms of the PK, but nonetheless, they measured that. They also looked at other thickening agents like guar. But they also looked at the disintegration time for 3 marketed products. So Trospi, Spasmex, and Spasmol. They see very large increases in disintegration time when you go from just SIF buffer to 2% HPMC. So they're like, maybe this is what's causing the negative food effect in this case, right? Just the reduction in dissolution and disintegration based on, the increased viscosity. So they also performed dissolution tests on Trospium. So they looked at the amount of drug dissolved versus time for various media. So they looked at CIF, 0.5%, 1%, 1.4%, and 2% HPMC. We'll not worry about the guargum at this time. Let's just focus on the HPMC. But so CIF would be more like the fasted state. And then at 2% fasted state intestinal fluid, 2% HPMC added would be something like thickening the contents more like the fed state. So the viscosity would increase quite dramatically, and you would see the dissolution really, really drop off. So if we look at our laser pointer here, you can see that the 2% HPMC has a very slow dissolution rate. And only about 25% of the drug or 30% of the drug is released in 120 minutes versus the standard intestinal fluid. It is all dissolved within basically 30 minutes, right? So we can try to use this to predict the negative food effect for Trospium. So that's going to be our activity in this case. So we're going to open up Trospium database in GastroPlus. We're going to navigate to the fasted record, and we're going to run that around the run that simulation and train our model. We're going to then take our trained model and where we've adjusted the permeability and apply that to the fed state in either using the 0.5 weight percent HPMC or the 2 weight percent HPMC dissolution data. And then we're going to use the Z factor to incorporate the in vitro dissolution data into our model. And then we're going to investigate further sort of reasons why the PK predictions might not be perfect in this case. So we'll get to that in a second, but let's open up our Trospium. So we'll go back to GastroPlus. I'm going to save my compound X record just to make sure I have saved all my changes for the future here. Then I'm going to go to File, Open Drug Database. And if I go back to one folder, I have my Trospium example already set up, and we'll open that up. So we've already sort of set up this database for you. The first record was generated by importing the structure from ADMET Predictor. And so from that, we predicted all the properties of Trospium hydrochloride, and it actually predicted a pretty reasonable permeability for this compound, which is maybe not correct in this case, but we'll get into that here in a second. And then the rest of the records are going to be the tablet and the fasted state for the 60 mg dose, and then the 60 mg tablet utilizing the 0.5 weight percent HPMC or the 2 weight percent HPMC dissolution data. So we'll go to the fasted record first. And everything is set up for us to run a simulation. We have the predicted properties. We have the experimental solubilities that we got from the paper. And then so we can run a simulation. And you'll notice with the ADMET predictor permeability, we're way over predicting the Cmax for this compound. So that's one thing, that's not quite right here. We're going to need to adjust the model. Rather than using the predicted permeability from ADMET predictor, we're going to have to adjust this permeability. And again, we can go back to our PSA to do that. That's probably the easiest tool in this case. We'll go select parameters. We'll go to the compound tab. We'll select PEF, click close, and then we already know that 0.72 is way too high for the permeability, so we'll set that as the upper bound. We'll select 0.2 as the baseline value, and then we'll select 0.05 as the lower bound. And in this case, we'll do maybe a linear again. We'll do a logarithmic. We'll select OK, and then we'll click Start. We'll save this. as the default name. And now it's going to do 10 simulations modifying the permeability of this compound and then predicting the PK. I forgot to remember what the Cmax of this compound, I think it's about 5.8, if I remember correctly, nanograms per mil. So let's click the spider plot and we'll go to the Cmax. And if we look at 0.0058 for the permeability, it looks like, about 0.013 for the permeability in centimeters per second times 10 to the fourth is going to be the correct value that's going to be predictive of our plasma concentration. So let's try it. So let's go back to the compound tab. Let's enter in 0.13. And let's go to our simulation tab, switch to the single simulation mode, click start. And you can see that we've got a pretty good match to our experimental PK data. So let's translate that to our other two records. I think we're a little bit behind in time, so I'm going to cut to the chase a little bit. We could do the 0.5 percent HPMC, but I already know that the 2 weight percent HPMC is closer to the stomach content viscosity and is going to give us the best prediction here. So I'm just going to skip directly to the answer, basically, you know, because we don't want to go over in time here. But so let's just go directly to this last record in the database, the 2 weight percent record. I'm going to save my changes, yes. And then we do want to add that permeability to the fed record. And I think we've already added it. So I've already added it in this case, so we already have it. So let's use the dissolution to predict the PK of Trospium. So there's a couple ways to do that. When you import in the dissolution data, you go to File, Load, and then the fourth item down is Load in vitro dissolution versus time profile. So this is where you enter in the in vitro data time versus percent released. So it's easiest to just paste this in from a spreadsheet, and we've already done this for time's sake. And this is the dissolution data from that paper that I had just shown in the slides earlier. Okay, so if we wanted to use this dissolution data directly, we could, but you have to set it up as a CR dosage form. So let's go to our dropdown and click CR. In this case, let's do CR dispersed or CR, CR dispersed. So we could then say, okay, let's use the dissolution rate data to predict directly the PK. We could go to start and then say, use the tabulated DSD data from the in vitro dissolution. And in this case, it's actually not that bad. Usually it doesn't work so well, but for whatever reason, in this case, it does do a reasonable job. However, this is not generally the way you want to model IR dosage forms because you know, the dissolution is dependent on the concentration gradients in the lumen. So in general, this is not the best way to do the prediction unless you're looking at a CR dosage form where the polymers are controlling the dissolution rate. So the best way to actually do this, in my opinion, and well, not my opinion, it's the fact of the matter, is to use the Z-factor dissolution model. So let's go to back to the IR tablet model. And then we'll go to the biorelevant solubilities tab. And that will allow us to change our dissolution model for the IR dosage form to a Z-factor approach. Of course, the Z-factor value currently is 0, so if we simulated this, we'd get a terrible answer, right? We have to supply some in vitro data to fit the Z-factor. So basically what the Z-factor model does is it lumps in the diffusion coefficient, the effect of the area of the formulation, the diffusion coefficient, the density of the particle, the the diffusion layer thickness. It lumps it all into one fitted parameter that will best fit your in vitro data. So let's go to fit in vitro data. And then we have to load our in vitro data file. So we go to File, Open in vitro data, and then we go to the 2 weight percent HPMC in the fed state. So this is our dissolution data that we just used to predict. So we're going to fit our dissolution data to that. Of course, you need to supply the dissolution, settings that were used to measure the dissolution rate. So the USP, it was a USP2 apparatus at 900 mils, 20 mgs were dosed to the apparatus, and the solubility was about 700 mgs per mil in the experiment. So we needed to add those to our simulation here in order to solve. So I'll click solve, and here we get a z-factor value of 5.7 e to the minus 8. So that's the dissolution rate as determined by the in vitro data. And then let's export this z-factor to our dissolution. Click OK, and then we'll run this simulation. And we'll get this prediction here. So this is how you would directly use the in vitro data using the z-factor model. So let's compare what we got in the fed state here versus the fasted state. So to do that, I'm going to click New Plot, and I'm going to set this aside. So I'm going to set the 2 weight percent HPMC in the fed state aside, and then I'm going to go back to our fasted tablet model, and I'm going to run a simulation for that as well. And I'm going to go to the Graph tab, and I'm going to click New Plot. And then what I'm going to do here is just compare the two. So they're not on the same scale. So to make them on the same scale, I'm going to click this little triangle icon here, which says Edit. And then I'm going to select the Axis tab. And then on the left axis, I'm going to set it to be the same as the 60 mg fasted, which was 6 nanograms per mil. So you can see, just based on the dissolution, we were able to predict about a 5-fold reduction in the Cmax and AUC for the negative food effect for trospium hydrochloride, just using the in vitro data. So this is how you're going to have to approach these negative food effects in GastroPlus. You're going to have to, supply some in vitro data to do the prediction. Now, why are we predicting too high of a PK in the fed state still? We've adjusted for the in vitro dissolution. Well, we've adjusted for the in vivo dissolution actually, because we were accounting for the change in viscosity. But why are we over predicting, right? And so let's look at that. So again, this was the prediction that they had made, Peter Langeth and that paper. They'd made this prediction, and we did a little bit better. I think we got about 5 and 1 for our, we got about the same prediction in the fasted state, but a little bit lower prediction for the fed state. So, but we got basically the same result as they did. And so they were looking at, how do we reconcile that? Why are we still over predicting? And so what they did was do a experiment in vitro looking at the ion pairing of trospium with the bile salts. So, and they had found that trospium alone with the bile salt formed ion pairs, and those ion pairs were more permeable than micelles. And these micelles are formed in the fed state, where in your diet, right, you're going to be eating some fats, right? So they simulated that with olive oil. So they added the trospium, bile salt, and the olive oil together and found that large micelles were formed, which kind of reduced the absorption by tying up the trospium and not allowing it to permeate the enterocyte layer. So this is something that is going to require in vitro data, right? And so this would be an input that you'd have to add to the model. And this is what Novartis has done as well with the CACO2 experiment, looking at permeability in FESIF versus FASIF buffer, or without FESIF or without bile salts. You could do that as well, but they were looking at just FESIF versus FASIF. And in this CACO experiment, they were able to measure these reductions in permeability, either caused by the ion pairing or effects maybe of transporters or other effects with the CACO2 cells based on the formulation. So they were able to input in these changes into their GastroPlus models and recover the food effects. So in this case, they modeled an 8-fold lower PEF and 8-fold sort of lower food effect. So they found success in using these in vitro experiments to predict the negative food effect. So that wraps up our presentation here. I'd like to turn it over to Kay, the moderator, to get into the last question and answer period. And I thank you for your attention. It's been great presenting here to you today. Kay, take it away. Sounds good. Sounds good.
Yeah, so Jim, here we go. Does the model take into account intestinal lymphatic uptake of highly lipophilic drugs when a high-fat meal is administered?
Yeah, so this is a question we get a lot. We don't currently have a method to have direct permeability into the lymphatic system. I think this is a question that comes up a lot with sort of like the lipid-based formulations. We don't have, our goal is to sort of come up with some additional options to be able to model those scenarios, but I don't think we've really looked at including that yet, but we do in the future want to add that capability. We do have, obviously, the we can do biliary excretion and reabsorption in our model, but we don't have the direct lymphatic absorption piece yet. But yeah, we're looking into it for sure.
Yeah, thank you, Jim. Just by the way, just like all a lot of features that requested by the customers, if we got more people request on certain features, that will move up their priority for our development team. So please send us comments or suggestions on our either the linking page or just send us email directly. That will definitely help with our development process. Also, maybe providing these features to you in a more timely basis. Second question, Jim, in GRDD's dosage form, can we use zero-order gastric emptying? So I just want to mention this term, the GRDDS. For those of you who are not very familiar with it, it's gastro-retentive drug delivery systems.
Yeah, so we have those formulation types in GastroPlus. So if you want to do a gastro-retentive formulation, we do have that model built into GastroPlus. So you don't have to change anything other than the dosage form type. So I mean, yeah, that's something you can predict as well with the GastroPlus. We do have that ability, so you can directly apply that model if you wish, and predict the basically the dosage form will stay in the stomach and release drug at the dissolution rate you provide, and then it will be emptied into the duodenum based on the transit time from the fed model. So we wouldn't assume that the liquid transit time is gonna, or whatever's dissolved in the stomach, that transit time stays the same. It's just that the dosage form won't empty the stomach. So yeah, that you can model in GastroPlus for sure.
Thank you, Jim. So next question, can you suggest media for simulated fat gastric conditions to conduct in vitro fat dissolution studies?
Yeah, I mean, I think you can go look at the literature, and there's a bunch of, I mean, you can go to like biorelevant.com and buy the pre-made FESIF and FASIF buffers. You know, you can get the and reconstitute them. These buffer concentrations are published in the literature too. You can look at FASIF V1, FASIF V2, and there's also FESIF versions as well, and those are freely available from suppliers. So I would recommend going and looking at those. If you can make it yourself if you really were that industrious, but it's not necessary. You can just buy it pre-made.
There's actually a following up question on the GRDDS from dosage form. So how do you differentiate the GRDDS with first order entering and zero order entering?
Well, so the gastric retentive formulation, the way our formulation works is that it assumes that you just have gastric release essentially from that form. So that assumes that the gastric dosage form will never transit away from the stomach, right? It'll stay in the stomach and then just release drug. So the transit time doesn't apply to the actual dosage unit. If you want the transit time if you want separate transit times for the solid dosage unit versus the dissolved portion of whatever's released, that's something that's not currently easily done, but you can, I guess there is some workarounds you could probably do with either the Weibull release rate or probably just you could do some workarounds with the MDD file functionality, which is the multiple dose data file that where you can sort of enter in different parts of the dose at different times. You may be able to do something like that. But in general, yeah, we don't have multiple transit times for the dosage unit versus the fluid. So, but the gastric release model assumes that the dosage unit doesn't actually leave the stomach.
Yeah, thank you, Jim. So would it be hard to predict the full effect for the PGP or BCRP substrates?
Yeah, so I think that's what we got into a little bit earlier. If the food effects are going to be caused by transporters, that's going to pose a whole additional level of complexity to the model that you're probably going to need some in vitro data to define what the effects are on PGP based on whatever the mechanism is. So I would suggest that you look into some in vitro experiments to try to determine how these transporters are being modulated, because our model isn't going to predict a priori how the transporters are going to be affected. So yeah, I could only really tell you that you're going to have to rely on in vitro data there.
Okay, thank you, Jim. And how to measure the mean precipitation time from in vivo data? Is it possible to use MM predictor?
Oh, so precipitation time is not easily predicted from structure, right? We don't have any, we don't currently have an in silico model based on structure to predict precipitation time. You can fit it to in vivo data, right? So that's one thing you can do, which is what we're trying to get to in this example here before we had the audio issues. So we're going to get into that example where we actually fit the precipitation time to the in vivo data. The other way you can do it is with in vitro data. Now, that's not always reliable. Usually the in vitro precipitation experiments over-predict the amount of precipitation that you'll see in vivo. But that's one option that you can go to, is using the in vitro tests as well. Although, as I said, that's not always accurate. So that's another option you have. And we have software, our DDD+ software, which is our dissolution software product. It'll allow you to fit precipitation constants to in vitro precipitation data. But yeah, those are really your only options. Either the in vitro parameters you can fit to in vivo data. Those are really your only two good options.
Okay, and then the next question is about lysosomal trapping. So lysosomal trapping affects which factors other than the Tmax, like volume distribution, T-half, etc.
So how will the lysosomal trapping affect the Tmax? I mean, it extends it, so it's always going to extend it, right? But It could affect, because you're talking about how much drug is stored in the different cells. It could also affect volume of distribution. We actually have a model built into GastroPlus to predict the volume of distribution. So using the new Lukachova method with lysosomal trapping. So in our software, we actually have that, that you can have that effect, and you can model that as well. So not just the appearance in systemic circulation, but if you want to model the actual volume of distribution change as well, that's available in GastroPlus. You would just select for the PBPK KP calculation, you would select Lukachova with lysosomes as the model, and it would predict that.
And we do provide the in vitro software to model that effect as well, right, Jim?
Correct. Yeah.
So we're going to ask two more questions. The first one, are pH shift, non-sync dissolution data useful as input, or are USP sync methods a better choice?
So in my personal experience is with a lot of class 2 compounds. Where I worked previously at Bend Research, we did a lot of amorphous dispersion type of formulation work and a lot of low solubility drug work. And in my opinion, for those drugs, I think the non-sync dissolution was much more valuable in really assessing what the dissolution rates were for those compounds. Settings that are more, I guess, applicable to dose to volumes that you would see in vivo, I thought were more interesting to look at. And if you built a dissolution model, you could extract the dissolution parameters from that data and provide reasonable inputs for the PBPK modeling. So in my opinion, for certain types of drugs like class 2, I think that non-sync dissolution is much underutilized. Now, a lot of people use a lot of sync methods, and those aren't, they're good for maybe release testing or whatever, but I think in terms of biorelevance and in terms of useful data to predict the real dissolution rate that's going on in the lumen, I think they maybe are a little simplistic. So I tend to think that those methods are better for certain situations. Obviously, for other classes of drugs that are highly soluble anyway, maybe not as important. It probably depends on the compound and the situation, is what I would say. But I think non-sync dissolution is much underutilized in the industry for sure. So that's my opinion anyway.
Thank you, Jim. And I know that you couldn't finish the two examples today showing the audience the positive and negative food effects. But if they look at your playbacks, then they will see that today we only are going to focus on the mean subject effects. I know that GastroPlus also provide a way for you to look into the population effects. And in the upcoming version of GastroPlus 9.8, we're gonna upgrade these population functions, right? Can you give our audience a little bit insight into what's the new function or what's the new feature we'll be providing in the version 9.8?
Yeah, so new in 9.8, we're gonna have quite a few new features for the population simulation. So we'll now be able to simulate intra-subject variability. We have always been able to predict inter-subject variability and generating our virtual subjects and sort of modeling the PK in a virtual population. But now we'll be able to also predict intra-subject variability in two different ways. We can do a simulation, so we'll just assume that there's variability on certain intra-subject parameters that are variable within a subject, which are things like transit time, pH, bile salt concentration, that kind of thing. And then we'll hold all the other physiological parameters constant, like radius of the intestine, length of the intestine, surface area, that kind of thing, all of that. So we're going to simulate intra-subject variability, and so we'll provide that as another mechanism to introduce variation into your population simulations. And then also we'll have the ability to do a simple version of that. If you've measured the intra-subject variability in the clinic, you can specifically post-process your bioequivalence statistics to include that amount of variation. So if you have, let's say, 10% intra-subject variability, you can add 10% extra variability on top of the normal inter-subject variability predictions in GastroPlus. So it'll allow you to do that both in the standard module, DDI, and in the DILI-Sim population simulator module. So yeah, those features are all going to be there. And the last, I think, feature there as well is you can now do, a lot of times people are requiring, 10 population simulations of a given size. So they may want you to do 10 repeats of the same population size. And so we can now do repeated population trials as well. So if you wanted to run a population trial 10 times, you can do that now automated. So that helps processing the data for FDA submissions and whatnot, and will help you improve your, I guess, how much manual work that goes into doing that kind of work. So it'll be automated for you. So those are the new features there.
Thank you, Jim. That's a lot of good features. I'm sure our users will be looking forward to the new release of the GastroPlus 9.8. Now I'm going to pass back to Arlene. Arlene, take it over.
Thank you, Kay, Jim, and Aditya. We appreciate you being with us today. I always find something new and valuable in your Q&A sessions. To evaluate GastroPlus for yourself or for your team, you can visit our website at www.simulations-plus.com. This concludes our webinar for today, but there will be an email with webinar replay links and the presentation slides going out to you immediately. We'll keep the conversation going on our LinkedIn page, and we look forward to seeing you tomorrow when Joyce Macwan takes us through GastroPlus for your virtual BE trial simulations. Thank you and have a great day.